Hello everyone, my name is Kiran and welcome to the module on password cracking. In this module, we'll learn about passwords, the way they are stored, different types of attacks used to crack passwords, and a couple of strategies used to mitigate against password cracking. Passwords are everywhere. I am a security conscious person with a very limited online presence, and even for someone like me, the last time I checked, I had close to 100 passwords. Passwords are very popular because they're simple and easy to use. They can be implemented easily, do not require expensive hardware or intensive computational power. But the very reason why they are popular also makes them vulnerable. In 1979, Robert Morris and Ken Thompson published a paper on password security and estimated that 86% of all passwords can be cracked. Since then, there have been numerous studies and different types of vulnerabilities in passwords have been discovered and exploited during that time. In terms of attacking passwords, there are two types of attacks: online and offline. Online attacks are the most obvious attacks. This is where you would just try to log into a live system by trying various passwords. As you can imagine, this method is not very efficient and it's time consuming. Also, most modern systems lock the account after a certain number of unsuccessful attempts. This strategy is also known as rate limiting. So it's unlikely that, unless you're extremely lucky, that you will be able to crack any passwords using this method. The other alternative, of course, are offline attacks. This is where, by some means, you obtain objects such as files that store passwords and then attack the information stored in these files or objects to retrieve passwords. How can you obtain these files? Well, there could be a number of methods. You can have access to, let's say, a file such as the password file or a shadow file used on Unix systems, or you could get access to a database. You may be able to launch an SQL injection attack and be able to retrieve stored passwords or password hashes or other forms of passwords in that database. So there are a number of ways you can actually get access to such lists of passwords. But in most systems, passwords are not stored in clear text. So obviously it's not enough to just get access to password files. Passwords are most often stored as either hashes or in an encrypted form. Therefore, it is necessary that once you have these raw data, that you are able to crack the passwords using various tools and techniques. As a person who is interested in digital forensics, this can be very important to know the various tools and techniques used, mainly because there are going to be cases where you will get access to an image of somebody's drive which stores a password, and it will be of crucial importance as a forensics investigator for you to be able to decrypt the password so you can find out more about the crime that you're investigating. So what is hashing? Hash functions, in simple terms, are one-way functions. Hash functions take a variable size input and map them to a fixed size output, which is also known as the hash value. Hash functions have some interesting properties. As already mentioned, they are one-way functions. That means that given an input text, it is relatively straightforward to compute the hash value, but given a hash value, it should be very difficult to compute the input text that gave rise to the hash value. Also, it's important that no two different inputs should be able to produce the same hash value. If this happens, this is known as collision, and this is considered to be a very serious weakness in any hashing algorithm. Also, it is important that for any small change in the input value, the resulting hash values should be very different. So it should not be possible for somebody to take hash values, compare them, and draw conclusions about the relationship or the differences between the input values. There are a number of hashing algorithms that are used, such as MD5, SHA-1, SHA-256, etc. I would encourage you to do some research on the internet to learn more about these hashing algorithms. But irrespective of their internal details, relative strengths and weaknesses, etc., essentially they all have the properties that we just talked about. So in terms of an offline attack, what happens is most often you will get a list of password hashes, and then different types of attacks are used to retrieve the actual password from the hash value. Obviously, as we discussed on the previous slide, it is not possible to have an inversion function which takes the hash value as an input and produces the password as output. So you have to use other methods. So a number of methods are used. The first one is called a dictionary attack. In this type of attack, you build a list of candidate passwords, essentially construct a dictionary, and then try and hash each one of those words in the dictionary and see if the hash value is contained in the set of hash values that you obtained. So if there is a match in the hash value, then you can conclude that whichever word in the dictionary resulted in a match is a valid password. The other type of attack is a brute force attack. Here you would systematically try all possible combinations. As you can imagine, this can be extremely time consuming, and also every additional character in the password exponentially increases the amount of time that is required to perform this attack. You could also have hybrid attacks where you start with a dictionary but also use some intelligent rules and then use brute force concepts to combine a word in a dictionary and come up with different variants, but not every possible variant. These rules are called mangling rules. So for example, you might have noticed that in some cases people will take a word, and then let's say the word contains a letter O, you replace it with a 0, or if the word contains a letter L, you replace it with a 1, or do some such transformation and create a password. So the mangling rules will try such transformations on the words in the dictionary and launch a hybrid attack. And finally, there is also what are known as rainbow table lookups. So what are rainbow tables? Rainbow tables are pre-computed tables of hash values. So instead of computing a hash value at the time of launching or executing an attack, what rainbow tables do is take every possible combination of characters and then pre-compute the hash values and store them in large tables. The idea here is that it is much more efficient in terms of time to search a table for a match as opposed to actually compute the hash values in real time. So this is also known as a space-time trade-off. So in a typical brute force attack, there's a lot of computational power that is necessary in order to compute the large number of hash values, but not a whole lot of memory is needed, or not a whole lot of storage is needed. Whereas in case of rainbow tables, you need a significant amount of storage to store the tables, but the computational effort involved in computing and finding a match is significantly lower. So depending upon the resources you have, you can choose one strategy or another. Also, Rainbow tables use a concept known as hash chains to further optimize the storage requirement. Once again, I would encourage you to go and learn more about hash chains. How has password cracking evolved? Well, traditionally speaking, there have been a number of tools which are very popular. These are Cain and Able, John the Ripper, etc. So these use the CPU power and essentially launch different types of attacks that we just discussed based on configuration and try to crack the passwords. But over a period of time, more and more tools have come up, such as Hashcat, Rainbow Crack, Cryptohaze Multiforcer, etc., which are taking advantage of the graphical processing units which are found on video cards in modern computers, and also trying to load the Rainbow tables onto very fast solid-state drives. So the comparison between CPU and GPU really is that architecturally a processing unit, the CPU, is composed of a limited number of cores with lots of cache memory, but they cannot handle a large number of threads. On the other hand, a graphical processing unit is by design made to perform a large number of intense computations. So they're composed of hundreds of cores that can handle thousands of threads simultaneously. As an example, you could have a CPU core that could execute 32-bit instructions, 4 32-bit instructions per clock, whereas you can easily find a GPU such as a Radeon HD 5970 that can execute up to 3200 32-bit instructions per clock. So how long does it take to crack passwords of various lengths? So if you look at a 10-character password, there are approximately 3.76 quadrillion possible combinations. If you were to try online cracking, and assuming that there was no rate limiting in place, and even with a large number of guesses such as 1000 guesses per second, you would need about 3.7 weeks to crack a password. On the other hand, if you were to use offline cracking but using the CPU based tools, which would try about 100 billion guesses per second, then you would probably get your password cracked at the most in about 10.5 hours. On the other hand, if you were to use modern GPU based tools and also take advantage of parallel multiprocessing clusters or grids, achieving up to 100 trillion guesses per second, then you would probably be able to crack the password in 37.6 seconds. So the message here is, while a 10-character password is probably longer than a password that's used by most people, today technology can easily crack such a password in a matter of seconds. So what can be done in order to make password cracking less efficient? So a couple of techniques have been used. One of them is known as salts. Salt is in essence a random piece of data that is used along with the password in computing the hash. So what this does is it essentially makes the password longer, and in cases where two different people are using the same password for whatever reason, the hash values are still unique because the salt value that's being used for the two passwords are different. So what salts essentially do is they require the rainbow tables to be bigger because they make the passwords longer in essence. And also when you're cracking a list of passwords, there's really no advantage in terms of cracking them, even if there was a lot of passwords which were repeated, because essentially the salt makes them unique. Another approach is to use expensive hash functions. So typically hash functions were designed to be fast, but when used in cryptography, fast hash functions are not necessarily secure, because it's also easy for somebody who's trying to crack the passwords to iterate through a list of candidates quickly. So a couple of algorithms have been proposed. There's something called bcrypt, which incorporates a salt, but not only incorporates a salt, but also uses an adaptive function, which means that over time you could tune the function to actually execute slower. So this is an interesting idea. So what you're essentially doing is you are making every computation of the hash value take longer, so there's only so many candidates that can be tried in any given amount of time. Scrypt, another slow hashing function or an expensive hashing function, takes another approach, which is it makes it costly to perform large-scale hardware attacks by requiring large amounts of memory. So while bcrypt essentially slows down the hashing function, scrypt makes it expensive in terms of memory requirements. So soon you would require so much memory that it will limit the number of candidates that you can try. So that is basically a high-level overview of various concepts. One other thing I also wanted to do here was to show you a demonstration of use of one of the tools. As part of this module, there is an exercise where you are required to download a couple of password hash lists from real breaches that happened a couple of years ago, 2012 to be precise, and you will be using tools to retrieve as many passwords as possible. So one of the tools I'm going to show here is called John the Ripper. Again, I would encourage you to go online and learn more about it. What you see here is are the various options for the tool. So essentially you can be providing custom word list using the word list option. There are different modes of attack. You could specify rules, the mangling rules that we discussed a couple of minutes ago. So there are a number of options. What we'll be doing here is we will actually be trying to crack the password for the SIFT, Sans Forensics account. What you see here is I'm trying to show you what's in the shadow file. So if you can see, the shadow file actually stores the password in a hash format. What we'll be doing is using John the Ripper and try to crack the password. So if you see, John the Ripper actually went through the file and decrypted the password for the forensics, the Sans Forensics account, and the password here is forensics. So there are obviously a number of different ways in which this can be used. John the Ripper, for example, can be used to crack a variety of different hashing algorithms. I would leave that as an exercise for you to go and try and find out. Once again, I encourage you to take the challenge, which is part of the module. There are also some useful resources which give you additional details about some of the topics that we just covered, but also give you links to various tools and word lists and so on and so forth. I hope you will have a fun time trying to complete the exercise and also learn about how to make passwords safer in case you are developing systems or applications that need to save passwords. Thank you for listening.